Okay, so we are going to take a look at another set of examples on how we can apply integration formulas and use integration techniques in order to evaluate integrals. So we're going to take a look at this one. Now the first thing I'm going to do, and you'll see it in just a bit, is first thing I'm going to do is I'm going to break up this integral. So I'm going to write it first as 8 over the square root of 64 minus x squared and then dx, plus a second integral, which I'm going to say is x over the square root of 64 minus x squared dx. Now, this is perfectly legal. You can do this because of the fact that this right here is part of the properties of integrals that surely you've gone over. You can break up integrals like this. So what I'm going to do is tell you how we're going to treat the second integral first. And that is that we're going to use U-substitution. All right, I'm just going to write U sub there. We're going to use U-substitution. But for this one right here, we're going to apply an integration formula. All right, now this is what the integration formula looks like. It says dx over, in this case, the square root of a squared minus x squared evaluates to be the sine inverse of x over a. The sine inverse of x over a plus c. So what we're going to do is we're going to pluck out what we know here. And that is to say that this right here is a squared and that right there is x squared. So what is a in this case? 8. And what is the square root of x squared? It's just x. So we're going to use this information to plug in here and here in our formula. But the only thing we have to remember is that this 8 needs to get migrated across. So now I think we're ready to take care of this integral. So the left part, the first part, is going to be the easiest. All right, because we just have to write this integral then as 8 and then sine inverse of x over a, which in this case is going to be x over the number 8 plus c. All right, we're going to hold off on the c because now we have to do our u substitution. All right, so we're going to say, well, u equals 64 minus x squared, and du will equal a negative 2x dx. So I just need to write in then a negative 2 here and a negative 1/2 on the outside. And now that I've done that, okay, I'm ready to do my u sub. So this right here represents my du, and this right here represents my u, all right? And now the integral that I'm working with is a square root in the denominator. So it's going to be something like this, a negative 1/2 on the outside, and then it is u to the negative 1/2 because it's a square root in the denominator, and then of course du. All right, so there's nothing really to this very simple integral. What does it look like? It's going to be negative 1/2, and then u to the negative 1/2 plus 1 gives you a positive 1/2. So it becomes u to the 1/2, all right, multiplied by the 1/2. Something like that right there. All right, so actually, no, not multiplied by 1/2, divided by 1/2, which becomes 2 over 1. So we end up with something that looks like that, okay? So when we clean all of this up, that's gone. We end up with a negative 1, in this case negative u to the 1/2 power plus c in this case. So now that we know what u is, well, we can write it over here. And I know I wrote plus, but now we're actually going to write minus. Okay, and in this case, u was 64 minus x squared, and then it's to the 1/2 power plus c. Okay, so the only other thing we can do here is rewrite it 8 times the sine inverse of x over 8 minus, in this case, the square root of 64 minus x squared plus c, your constant of integration. So really nice. You know, you have to apply one of the integration formulas and then use substitution. All right, so let's go ahead and take a look at another example. This one right here is going to be another U-substitution problem. However, this one's a little bit different in the way that we're going to treat it, okay? I'm starting to see something already that maybe you don't, and that is that right here, this right here is going to be our U. So let's say that U equals the natural log of x to the third power. Now I'm also going to take and apply the laws of logarithms and say, well, U is actually equal to 3 times the natural log of x, okay? And that's very important here, all right? That is very important. Let's go ahead then and take our du, our derivative. Well, we know that 3 is going to be in play, and we know that the derivative of natural log is just 1 over x dx. So what is du then? 3 over x dx. So I've got the 1 over x part there. I'm missing a 3, so I can make it happen. I just multiply by 3 and 1/3 on the outside. Okay, and now I think I'm ready to do my integral. So let's go ahead and put a ring around what we know. And I forgot my dx there, but let's put the rings. I know I have my my u, and now this right here represents my du. Okay, so now that I've got that, all right, let's see what I can do. I'm going to have 1/3 of the integral of du over u, which just evaluates to 1/3 of the natural log of the absolute value of u plus c. Now this one may look a little bit interesting to you when you do the back substitution, because you're going to have a natural log embedded within a natural log, but that's okay. All right, so let's see what that looks like. All right, there we go, plus c. All right, so that right there represents the integral that the answer to the integral anyway that we were dealing with. Really nothing to it, and I think we've got time for a couple of more examples. In this next example, we see that we've got a sort of problem that has a polynomial, in this case a trinomial of the second degree, in the denominator. And it's actually a really nice problem, okay? Well, what I'm going to do is I'm actually going to apply this technique for the tangent inverse. And the tangent inverse requires that you have some kind of two squares being added, a sum of squares, if you will. So what we're going to do is we're going to kind of do completing the square technique. So you're starting to put together, you know, maybe everything that you've ever done before. So we're going to complete the square, if you will. And that's how we're going to approach this problem. So I'm going to take the x squared plus 6x plus 13. I'm going to set it equal to 0. I'm going to complete the square and rethink the way that this one looks. So let's see here. I have x squared plus 6x. Let me fix that for you. Plus, and in this case, parenthesis square, and I'm going to set it equal to negative 13 because I moved the 13 to the other side, plus parenthesis square. Okay, and so what I fill in here is the fact that I have half of my b term, in this case half of 6, which is a positive 3, and what I do to one side I must do to the other. And so I'm going to end up with, in this case, if I pull all of this together, x plus 3 quantity square equals negative 13 plus 9, which is what? Negative 4. So I have an x plus 3 quantity square equal to negative 4, which I'm going to move back over, because now that I've completed the square, and I'm going to rewrite my integral. So I'm going to have dx over the quantity of x plus 3 square plus 4, which both of these now are perfect squares. So when I think about them in isolation, okay, when I think about them in isolation, I'm trying to identify my a and my x, if you will, all right, which we're going to get as the following. Okay, this right here, the square root of x plus 3 squared is just x plus 3. And then the square root of 4 is just 2. And we're going to use that and apply that in the formula. Okay, so let's see what we get. All right, we're going to take our 1 over a, which in this case is going to be our 2. And then this is going to represent or model what we call x. I'm going to put that in quotations. All right. So let's go ahead and take a look then. If we follow the rules here, we're going to have as our answer to the integral, as we've evaluated the indefinite integral, 1 over 2. And I'm going to say tangent inverse. And in this case of x plus 3 over 2 plus my constant of integration, c. All right. And now that I've done that, I've actually evaluated the indefinite integral by applying the formula. So again, the algebra footwork probably was the toughest, but once you've got it down to where you need it to be, it really wasn't much to take care of. So let's go ahead and take a look at another example, very similar, but in this case, this one's going to be for sine inverse. So let's take a look. Okay, so we're going to take a look at this one, and we're going to again apply the same concept of that completing the square. So I'm going to say in this case, x squared minus 4x plus a parenthesis square equals a positive 5 plus a parenthesis square. And I get all of this because I set that part that I underlined in red there, set it equal to 0. So I'm kind of just jumping ahead here. All right. What do we put then in the parenthesis? We put half of your b coefficient. So in this case, half of -4 would be -2. And it's very important that you keep the sign there because then it tells you what to write when you're doing your square portion. In this case, x minus 2 square equals 5, and then -2 squared is 4, 5 plus 4, 9. So you end up with x minus 2 quantity square equals 9, and then you of course bring this back over, and you can rewrite your integral. And so when we rewrite that integral, what does it look like? We get dx over, in this case, the square root of x minus 2 quantity square minus 9. Okay, and we pluck out what we know. And in this case, again, I'm going to put this x in quotations. We say our x component is x minus 2, and we say our a component is 3 because it's, again, we're just taking the square root. Now that we've got that, we have enough information to solve the integral. And that is to say that we have the sine inverse of x, which in this case was x minus 2, over a, which in this case is 3, plus c, our constant of integration. And then after that, there's really nothing more to do. All right. So what I want to reiterate and what I want you to understand is there are a multitude of integration formulas that you can apply and you can use. All right. Look up a table of integrals, look up, integration formulas. If you're using a textbook, typically they like to put a bunch of charts maybe in the front of the book or the back of the book. And I know I've seen in some cases in some textbooks, they're like little cardboard, or not cardboard, but tag board that you can kind of rip out on the perforation and then maybe stick it into a notebook or a binder. So there's a lot of formulas. We only scratched the surface on this second video and really on the first video of the formulas that you can apply and you can use. All right. As always, I hope this video was helpful. And remember, like and subscribe.